to-do list application. And you'll see TDL.client, TDL.server are the two halves of the application. This thing right here, to-do, is sort of an artifact that when I created for you. Change my mind about the call. Okay, and then right under TDL here, directly inside the browser, inside that package, is the XML file I mentioned that defines the module. So you can see that it inherits a couple of modules, so it's getting code from a couple of modules. And it's an entry point class. It's saying the module has an entry point. And what that means is, if the module has an entry point, when the module is loaded, the entry point is called. Now, when would a module be loaded? Well, what makes it be open? Basically, we packaged up this code. There's a client component, there's a server component. The server component is just sitting on the server already. Nothing special. That's how the server works. It's the client component that has to be loaded. So when would the client component of this module be loaded? Not exactly. Anybody else have an idea? Why would you be accessing the client part of this application? What would cause the client part of this application to be of interest to the browser? Well, it's when you refer to it as a web page. So down here is a web page, to-do list.html. And you can see it's just a regular HTML page. It links to a CSS. It has a title. It has a body it's basically empty. This is the key thing right here. So that code refers to a module. That's referred to in a different way. But anyway, TDL.to-do list is referring to my to-do list client module. And so when this web page is loaded by the browser, the module is accessed. And this link will work whether we're in development mode or not. If we're in development mode, it'll use a plugin to deal with that link. If we're not in development mode, it'll just download and compile JavaScript. And you can put as many of these references as you want in a web page. When you do that, each module is loaded, the client code is loaded and run. Well, it's loaded. And if it has an entry point method, that entry point method is called, executed. And the job of the entry point method is to modify the web page in some way. Now, when we load our to-do list, what does it do? How does it modify this web page when we load this module right here? Right, it goes and replaces the body with the to-do list code. Now, what if we had 3 modules? Why would you ever have, say, 3 modules loaded into the same web page? Pop-up ad. Okay. But what if they all go and start trying to replace the body with their, you've got a to-do list, and you've got a forum, and you've got a calendar or something. What if they all 3 load up, run their own load methods, and try to replace the body with those 3 things? Why would you ever want to do that?
Depending on different web browsers.
No, well, I mean, you certainly have web browser dependencies, but well, yeah, the thing is, you want to maybe you want to have have a to-do list and a calendar and a forum all on the same web page. But you certainly don't want them appearing on top of each other. But what you can do is, you can put a little bit of markup in the body. You can put div tags with IDs, say ID equals to-do list, div ID equals forum, div ID equals calendar. And then when the module gets loaded, it doesn't necessarily, you can write it to replace the whole body. You can also write it to replace a div. So if you have a bunch of little different widgets you'd like to be able to place into web pages, you just refer to the modules that you want to load in, come up there, and then when they run, they can go paste their bit anywhere they want to. Basically by looking up an ID and replacing the, looking up a div by ID and replacing that with the to-do list or whatever. So you can end up with a page with all three things. And you can put arbitrary HTML in here, with little placeholders for where the widgets are going to go. So that's how that goes. And then if we go look at the actual code up here, here is client. Inside the client we have to-do list.java. That's the entry point class. So you see right here it says implements entry point. All that means is to implement entry point you have to have it on module load. So the web page is loaded. The modules, each one's on module load is run. And this on module load creates all the, creates the table and the buttons and everything, and pastes them into the web page, replaces the whole body of the web page. But we could easily arrange for it to replace just a small piece of the web page. So we could put several to-do lists on the same page if you wanted to. Maybe one for home and one for work. As long as we provide a place in the HTML for them to be plugged in. So that's the client-side code. And inside the client-side code, there are these, that's a call to the get task service on the server side. And if it fails, we just pop up an alert. If it succeeds, we do something else. Okay, and right now, on the server side, we're keeping everything stored away in session variables. What I'm about to do is show you how to change that and actually use the Google Data Store. Okay. So this is like the third day in a row where I've talked about the high-level structure of modules. That's okay, but I'd like it to be the last, so we'll see if there are any questions I could answer about all this. And I warn you, when you go look on the web and try to figure out how to do it, there'll be examples in Java, there'll be examples in Python, there'll be examples that use the window building tools that we've been using, there'll be examples that don't. So just be aware, at least look at the Java examples. You see some code that doesn't look like Java. All right, well, let's talk about databases. All right, I want you to imagine that you've created a to-do list application, and you've deployed it on the Google App Engine, or some way, you've deployed it. And it's become wildly successful. And everyone's phone in the world has a to-do list application on it. And they're constantly putting things on and clicking done. And you've got this database up on the cloud that's keeping track of the state of everyone's to-do list. So that when they, every time they log in, it can populate with the right things. When they add, they delete, the database is modified. So imagine that we've got a single MySQL server, and that's the state of our application. So we've got billions of smartphones, all contacting server, some Tomcat server, let's say, and then there's a database backend. What's the problem? What engineering issues can you see? How responsive do you think their smartphones are going to be? They're going to be slow. Why is the application going to be slow? Too much. Right, you've got billions of phones all trying to contact the same server. And of course that's going to be slow. It's a bottleneck. You got one Tomcat server, and you've got all these things trying to make connections to it. You can't support that many connections. They're going to be drop connections and waits, and it's not going to work. So we need to find a way to scale the application. So one way to scale an application is horizontally, or not horizontally, vertically. Vertical scaling. And when you do vertical scaling, what that means is you have some little computer running Tomcat. And what's one way we could deal with this resource limitation vertically? Right. We make it a big Tomcat server, a big computer, with faster internet connections, lots more memory, multi-cores and all that. Make a bigger one, that a beefier Tomcat server that can deal with things faster. Okay? So that might work. Why might it not work? Say it again. Right. I mean, you can make it to a certain size, but you can can't make it arbitrarily large. What are some other problems with this single Tomcat server, no matter how beefy it is?
What happens when it crashes?
Right. When it crashes, your whole application's toast. Okay. You may have billions of users. You might have 1 billion users in Asia alone. What's the problem with this Tomcat server sitting in Utah? Right, now you've got latency problems. You've got, why not put the server in Asia or something? And so that's what horizontal scalability is. And horizontal scalability says, okay, you can have big computers, but what we need is lots of them instead. So horizontal scalability says, let's just put a bunch of servers all around the world. And when your application needs to contact one, it just contacts one. Whatever one's closest or most available, or you get to fastest or whatever, you contact one, and it serves it, it does it for you, okay? So now we can have lots of cheaper servers, put them all over the world, locate them where the electricity is cheaper, where the air conditioning is cheaper, whatever. Somewhere cold with hydropower is a popular place to build things. Build these data centers. And then, if our goal would be, you've got a bunch of servers, you got this application, and it's working just fine, and then you double your number of users, and suddenly the response time has been cut in half. So what do? Add more servers. What we want to be able to do is double the number of servers and have that double have the response time. That would be our goal. All right. So that's the idea, and Google maintains, and Amazon and so forth maintains lots of big server farms all around the world for this purpose. So this is our web server now. But we still have our SQL database that keeps track of all the to-do lists, and we have all these servers banging on the SQL server. Okay, what's the problem there? Right, now my database is a bottleneck. Okay, so yeah, there are lots of Tomcat servers, lots of web servers for all my clients to contact. But if they're all depending on the same machine up here for with SQL services, it's the same type of bottleneck. And again, we could try a couple ways to scale it. We could try to make this bigger, beefier, and that works. works to a point. But in the end, what we're going to have to end up doing is replicating the servers as well. So we just don't have to replicate web servers on server farms. We've got to have multiple databases. Now, what issues can you see with having a whole bunch of databases if these things can all contact? What's going to be the difficulty with this picture here? Right. The problem is synchronizing information. Do you try to keep all the information on all the servers? Do you keep part of the information for each? Part on each and not have one server that knows everything? There are various designs you can try. And there's been a lot of experience with researching these issues and trying to figure out how to replicate across multiple servers. But the goal we want to have, so we're going to focus on this type of issue. Okay? This is a little bit simpler. What's simpler about replicating the servers down here? Okay.
Data's the same on all the servers.
Right. Basically, the servers down here, they're just running programs. You can easily load the same programs. You don't change that all. They don't contain state. Right? You don't want to use member variables. I told you, don't use member variables in your servlet classes, and don't use the context. Servlet context is sort of a poor-man's database. Well, it's not something you want to use when you can have a database because you don't want to have state in these servers down here. All the state's up here. So this is where the challenge lies. So what we want to do is make it. Our goal would be to make it so that if the time it takes to access a database is too long, we want to be able to double the number of not SQL servers necessarily, but number of database servers and bring that back down. So now I'm not going to get into the difficult distributed programming problem of how to actually make all this work. But let's figure out what kind of features in the database would make this fail. Okay, so let's think of the first problem. Let's put down a schema for what a database would look like to keep track of to-do lists. So you've got your to-do list application. How many tables would there be? Okay, so there'd be users. And the users table, let's see, what fields might it contain? Maybe some ID, some unique ID. To identify the user, maybe the user's name, login information, password, something like that. So you'd have that table, and it would contain an entry for every user that you have. And then the other table would be maybe tasks. I made it so big. And what would be in the task table? Okay, so there would be, I'll put this first, a UID and a task. Okay, so if I have 10 tasks, this table would have, my UID is 7, there'd be 7 rows that have a 7 UID, and then some other person would have rows for, with a different UID. So this would have 1 row per user. How many rows would this have? So if there are 1 million users that each have 10 tasks, there would be 10 million rows. Basically, you just sum over all the users, all their tasks, and that's how. So that table could be quite big. This table could be big. I mean, if you have 1 billion users, that table has 1 billion entries. This one, if every person averages 5 tasks, this would have 5 billion entries. Big thing. Okay. So let's think first of all about writing. So a very common operation would be, we have a task we want to add to our list. So around the world, we have lots of smart clients. So we have all these clients, right? So this is the client level. And they need to add an item to the task table. Okay? And what's that going to take to do if you write this in SQL? What are we going to have to do? We're going to go through, you know, there's going to be a layer here of the web servers. So let's say we contact the server, we say add this task to my list. What's it going to have to do? Basically you say, you give it your login name. Okay, so you're going to have to go to this table and look up the ID. And once you know this ID, then you can add to that table. So let's ignore the read problem. So we got the ID, we know our ID number, we need to add to the table. Okay, so what are we going to do about our replicated databases here? Okay, in fact, let's make this a little more interesting. Let's say we're adding 2 tasks at the same time for someone. Okay? So if you're adding 2 tasks at the same time, well, let's do one first. You're adding 1 task. How are we going to do it? We want it to be fast. Yeah. One idea would be just add it to 1 and be done. Okay? Now what problem do we have? Okay, some of the, some tasks are here. No one database contains all the tasks. It just contains some of them. Now you could, if you wanted to, behind the scenes, over time, it would take a while, is you could propagate copies elsewhere if you wanted to. And you probably want to do that for reliability purposes, so if one goes down, you don't lose it. But it's a lot simpler if we want to write 1 task, to write it, and then let the database worry about propagating it, than for us to have to write them all. That would be a real bottleneck there. So let's just put it in 1 place. Now, what if we want to write 2? 2 in a row. And if you're doing 2 things like that, what do you need to use? What do we learn? If you're writing database code, it has to do 2 operations, and you want them to be atomic. You have to either both happen or both not happen. The transaction. So, what issue do you see with doing a transaction on this distributed database? Do you lock the database down, write your 2 tasks, and then unlock it? Why would that not be a very good solution? What's that? You've got billions of users. Maybe there's 10,000 at the same time trying to write tasks to the database. You clearly don't want me writing my task to the database to prevent somebody in Asia from writing a task to their database. And so if you go too far with synchronization, that becomes a real bottleneck right there. So that's something else to consider is synchronization. What role does it have in all this? Now let's do a query. Let's suppose I want to get all my tasks. So basically do a query on this table that says, give me back all the tasks for UID 7. Okay? And let's suppose that this database is in some state where some of my tasks are here and some are there or some are there. Or maybe they're in a state where you've got, maybe the tasks have been replicated and there's the full task list. Let's think about that. The full task list is stored on a dozen different disks. How can we make that fast? Right. You can distribute the load. So basically you can have, if only part of the database is only in each one, you can have them run in parallel and run the query on their data, and so they're all working in parallel and then sending the results to you. Or if the whole database, if the whole table is replicated across some disks, you can have each one do a piece. I'm not saying your code has to control that, but the code that's controlling this distributed database, you can run the query simultaneously on multiple servers and have one server give you the first chunk while the next server is giving you another chunk and the third server is giving you a third chunk. And then they all come back. Because we want to make it so that if our response time is too slow, we can make it faster by having more servers and having more parallel. And
So what happens when you write something to the database and you depend on it to cascade it to the others? What happens if you write something and then query it and it tries to pull from a database that doesn't have it?
well, it's up. I mean, I'm sweeping a lot of stuff under the rug. There's software that's coordinating. These things talk to each other, and there have to be some knowledge of which servers contain which servers contain which tables and which parts of which tables. So it's not an easy problem. But the idea is that it's possible. If your data is replicated across a bunch of disks and the system knows that, then running a query means it can be run in parallel. Okay? But as you mentioned, the need to do synchronization, the need of transactions can cause a bottleneck. So if you ignore the need to synchronize, then we can see that if we got a bunch of clients that want to write at the same time, they can just write to different servers and let the servers figure it out. If you've got a bunch of clients that want to look up something at the same time, they can run in parallel. This guy's query can be running here, this guy's query can be running here, or this guy's query can be running in 3 places. And as we continue to scale horizontally, we get better performance on those reads and those writes. Unfortunately, if we insist on transactions, if we insist on consistency, we don't want to get in a situation where we write a task, and then we go read our task list, and it doesn't show up on it because it hasn't propagated to those servers, is what you were saying. Then we got a problem. If we want to put transactions on top of this, then we start to get bottlenecks, and transactions cause bottlenecks. So transactions are things to avoid if we can. We want to design the system. We want to design the kinds of demands we can put on the database so that horizontal scaling will help us. And horizontal scaling helps us with writes. It helps us with those reads. But we start to lose the scalability when we have transactions. There's one other thing that will kill, that doesn't scale well, and that's joins. What's the problem with doing a join? Suppose you have to join these 2 tables. We've got this replicated database now. We're trying to do a join. Yeah, you've got the tables are scattered all over the place. Basically, to form the join, you've got to have access to both tables. And the result of the join is gigantic. It can be gigantic before it's filtered down. So joins as well. Joins are also something to be avoided if you're trying to have the scalability. So just with that little background, again, that's a class in distributed programming. You learn about the algorithms that help keep all these databases in sync. We get to the Google Data Store. Now, does Google face these issues here? Yeah, it has massive amounts of data and massive numbers of users all trying to work at the same time. But lots of other entities do as well. And so the Google Data Store is an example, the approach that they use is an example of approach that lots of other big companies use. And the distributed database they use the NoSQL model. So their data store is not a relational database like we're used to. In particular, there are no schemas. So you don't design the tables and then start filling them up. There are no schemas, there are no tables. Okay? Second of all, there's a query language, but there are no joins. So if you've got to take, that limits, with SQL, when you do a join, you're doing a lot of processing on the database server to produce perhaps a small amount of results. To do the similar sort of thing with Google Data Store, you just got to do the processing somewhere else. On the web server or on the client. It's taken out of the database in order to make the databases more scalable. They're called joins kill scalability. And then another thing about the Google Data Store is there are no schemas, no tables, there are no joins. It does not guarantee the asset properties. It does not guarantee consistency in all cases. And what that means is it is possible to do a write and immediately do a read and not get the thing you've written back because you read from a different place where you wrote it. Now, if you want consistency, you can get it, but then you're limited in how fast you can write. So if you want consistency like we're used to, strong consistency, then you're limited to 1 write per second. Which means essentially writes happening at human speed. If you're willing to give up on consistency, you're willing to relax the consistency constraint, be willing to see stale data when you read, then you can write faster. Now that sound, at first glance, that sounds like a bad trade-off to make. Why would you be willing to put up with inconsistent results at all? Now, but think about our to-do list application and tell me, where would you want consistency? And where would you be willing to see inconsistent results?
I think that if you're writing, you're willing to see inconsistent results because you're often already working with the data anyway, so why do you need to pull it back immediately?
Okay.
Hopefully.
Okay. So, one idea is to design your application so that the consistency issue doesn't matter. So, for example, if we go and write something, we're doing our to-do list, we add something to it, we write it to the database. We don't need to turn around and read it back in because we've got a local copy. But suppose that what you did was you wrote it, and then you rebooted your smartphone real fast, and then you went to read your to-do list back, and the thing you just wrote didn't show up on the list. Maybe you refresh it 5 seconds later, it shows up, because it took that long to propagate. Okay? Is that something you're willing to put up with as a user? Or would that disturb you? You just save something in your to-do list, and then you reboot your machine, and you refresh your to-do list, and the thing isn't there.
And how often are you going to be rebooting your machine every time you add? I mean,
Yeah.
well, maybe it's not that big a deal. When you scale it to other users, though, and you're trying to sell a product, people are going to see it as a bug.
Yeah, they'll see it as a bug. And so there, you want consistency, and you can pay the price. So you can say, okay, whenever I go and look at, when I add something to my to-do list and read it back, when a given user adds their to-do list and then reads it back, I'd be willing to, I want to have consistency. And so I'm willing to pay the price. And the price is I can't update very often. I can only write once a second. Is that okay? How fast can you add things? Yeah, you might add things once a second. So that's perfectly fine. But what we don't have to do is say the entire application has to be consistent at all times. In other words, this guy in Utah and this guy in China, does it matter whether they are synchronized? I mean, the guy in China is not writing to my to-do list, and I'm not writing to his. Or to put it another way, suppose there's a master application, a master page that showed me everyone's to-do list. And someone, say I write to my to-do list, and then a fraction of a second later, the administrator pushes a refresh button and to see what's on my to-do list. I want to see what's on Joe's to-do list, so he pushes the button. And my thing doesn't come up on his refresh button. It doesn't show up on his list. But 5 seconds later, it does. We're going to put up with that. And if we're not willing to put up with that, we have to synchronize the entire application, and then people can, worldwide limit will be adding 1 to-do item per second. That's not going to work. So what you do at the data store with the NoSQL approach is you decide where you care about the synchronization, where you care about consistency, and where you don't, where you're willing to wait a while to get the full view of things. So the administrative interface would be a case where you're willing to wait a while. You know, let's say there's a forum system. People are publishing things on the forum system. Is it a big deal if somebody over here sees someone's post 5 seconds before someone over here sees it, because they're talking to different versions of the database? Probably would never find out that was the case. You think that's perfectly natural. On the other hand, if you post to a forum and you don't see your post come back right away, that would bother you. So you want to keep your post synchronized, the post of a given user synchronized, because they can only post so fast. And don't necessarily keep it strictly consistent with everyone else's post. Eventually, they call this eventual consistency. Eventually, all the updates will propagate through the system and you'll see them. Just that you might not see them right away. Okay? So that's something that's put on you as the designer of the application. Where do you want to enforce consistency and give up on and restrict your update speed? And where are you willing to relax consistency and be able to update quickly? So let's take a break and we'll show you how this all works out.